For calculation of steady state error for P controller. For second order transfer function, this is transfer function, which is GS equal to 10 over S squared plus 5S plus 6. Recall that for a closed loop system, ESS equal to limit S to 0, open bracket S1 over 1 plus GS data input as close bracket. For unit step input, we are using this equation, which is data input S equal to 1 of S. Thus, ESS equal to limit S to 0, open bracket as 1 over 1 plus GS, data input as close bracket, and finally we will get limit S to 0, open bracket 1 over 1 plus GS, close bracket. So, for GS equal to 10 over S squared plus 5S plus 6. So it will become 1 plus GS equal to 1 plus 10 over S squared plus 5S plus 6. And finally, we will get S squared plus 5S plus 6 over S squared plus 5S plus 16. Therefore, ESS equal to limit S to 0, open bracket as 1 over 1 plus GS data I as close bracket. So we solve this equation and finally we will get 0.375. For P controller with gain Kp, the closed loop transfer function becomes G0S equal to GPGS over 1 plus KPGS, and we solve the equation and finally we will get 10 Kp over S squared plus 5S plus 6 plus 10 Kp. Alright, so for steady state error, 1 plus GS equal to 1 plus 10 Kp over S squared plus 5S plus 6 plus 10 Kp. So we solve this equation and finally we will get S squared plus 5S plus 6 plus 10 Kp over S squared plus 5S plus 6 plus 20 Kp. So therefore, ESS equal to limit S to 0, open bracket S 1 over 1 plus GS, data I as close bracket. So we solve this equation and finally we will get 6 plus 10 Kp over 6 plus 20 Kp. For stability of the system, use zero Hurwitz criterion. So we solve, and after that, the final answer we will get ESS equal to 6 plus 10 Kp over 6 plus 20 Kp. Right, so we move to calculation for PI controllers. So in PI controller, closed loop transfer function with Kp and integral gain Ki over S, the closed loop transfer function becomes G0S equal to Kp, open bracket S plus 1 over Ti, close bracket Gs over S. And we solve the equation and finally we will get 10 Kp, open bracket S plus 1 over Ti, close bracket over S, open bracket S squared plus 5S plus 6, close bracket. For steady state error, 1 plus GS equal to 1 plus 10 Kp, open bracket S plus 1 over Ti, close bracket, over S, open bracket S squared plus 5S plus 6, close bracket. And we solve this equation and finally we will get S, open bracket, S squared plus 5S plus 6, close bracket, over S, open bracket, S squared plus 5S plus 6, close bracket, plus 10 Kp, open bracket, S plus 1 over Ti, close bracket. Therefore, ESS equal to limit S to 0, open bracket, S 1 over 1 plus GS data I as close bracket. And we solve the equation and finally we will get 0 over 10 Kp, 1 over Ti. And final answer, we will get 0.
Hi, my name is Nurul Nabila binti Mahswan, CE2200X7. So now I will show the simulation for Simulink.
Okay, I open the Simulink, I open the MATLAB, so over here is Simulink. Now we show how we do the simulation. First of all, we open the library browser.
So now
Then,
I will show the simulation for Simulink.
Then we can click over
Hi,
here,
my name
click
is
the time,
Niruna
then just
Binti
type what we
Maswan,
need. So we need
CE22007.
tab,
So now I will show the simulation
then we
for
need
Simulink.
some,
Hi, my name is Niruna Binti Maswan,
we need tab, we need some, we need
CE22007.
PID
So now I
controller,
will show the simulation for Simulink. Hi,
then we
my
need
name is
transfer,
Niruna
transfer
Binti Maswan,
FCN,
CE22007. So now I will show the
then we also
simulation
need scope.
for Simulink.
We need scope for
Hi, my name
showing
is
the
Niruna
graph.
Binti Maswan, CE22007.
So just,
So now I will show the
okay, now
simulation
we click
for
the
Simulink.
PID.
Hi, my name
We
is Niruna
click the
Binti Maswan,
transfer as FNC
CE22007.
first.
So now
We
I
change the
will
value that we need, which
show
is
the
over here,
simulation
10,
for
then
Simulink.
1,
Hi, my name is Niruna Binti
5,
Maswan,
and
CE22007.
6.
So now I will show the
Apply,
simulation
okay.
for
Then we make,
Simulink.
eh,
Hi, my name is Niruna
we
Binti
make
Maswan,
the
CE22007. So now I will
bigger.
show the
Then we
simulation
can auto
for
tune the PID.
Simulink.
The reason for you
Hi,
use
my
Simulink
name
for
is
auto tune the
Niruna Binti
PID.
Maswan,
Over here, we click the
CE22007.
tune.
So now I will
Now it's
show the
compiling.
simulation for Simulink. Hi, my name is Niruna Binti Maswan,
We obtain the plan model.
CE22007. So
Export, and you
now I
can
will
see over here
show the
the value for
simulation
P.
for Simulink. Hi, my name is Niruna Binti.
Okay, for discussion, as we can see in table 3.2, we clearly see the value that we get for Ziegler post and auto 35 minutes. The control relation to the signal is measured by the proportional gain Kp. The higher value of Kp is a stronger response, while the lower value is more subtle relation. From table 3.2, the higher value is auto-tuning by in response to the error signal. It suggests that the control system will behave more aggressive, which could lead to faster but potentially less stable control. Next, the integral gain Ki is determining the ability of controller for eliminating steady-state error. In this case, the auto-tune value got the lower value, which is 40.01, while Ziegler-Nichols got 24.28. Okay, for D, which is the derivative gain Kd providing damping to the control system, reducing, overshoot, and stabilizing the response of control system. If Kd value higher, it will enhance the damping effect. Meanwhile, the lower value dismiss our auto-tune got the higher value, which is 2.449. Meanwhile, Ziegler equals got 0.74075. PID controller excel in many scenarios but face challenge in non-linear systems. They may struggle with quick response to fluctuation and exhibit difficulty in correcting overshoot. Implementing feed-forward control for steady-state error and addressing issues arising from the linear nature of PID controller in non-linear systems is essential. Additionally, the derivative term can amplify higher frequencies, causing significant difference in system output.